All right, hey everyone, welcome back. Today we're going to be talking about atomics, which are a pretty interesting topic and something that I've been learning a lot about recently. In particular, I recently learned that when you use atomics in C++, in some cases the compiler can actually emit mutexes or more traditional locks kind of under the hood into your code. And I thought that was pretty interesting because usually when you're using atomics, the whole point is to not be using a mutex. You might be using atomics to do some lock-free programming, to implement a lock-free queue, for example. And the typical motivation for doing that is because you previously were using a regular mutex to protect some shared data, and there was too much contention for that mutex between all the threads that you have running. And so you might reach for a lock-free implementation that makes different trade-offs but can improve performance in these cases. So atomics, are very interesting, and I wanted to just kind of talk about them a little bit. We'll take a look at the C++ standard library and the atomics support provided there, and we'll check out this function called isLockFree, which is kind of interesting, and then we'll explore actually how under certain circumstances the compiler can emit locks into the code. I'm not very well able to actually give a full introduction to atomics because, frankly, I'm not an expert and I don't have that level of understanding. But my kind of very layperson's understanding of them is that they are a low-level primitive that is offered by the hardware, and it's explicitly meant to support multi-threaded programming and multi-core programming. And using the primitives provided by atomic operations, you can build on them to build higher level tools and primitives. Like, for example, with atomics, you can build on them to build a spin lock, for example. That's a pretty basic use. That's maybe one of the first things you might implement if you're writing an operating system, is a basic spin lock, and you actually need atomics to do that well. I don't think I'll dive deeply into why, but that's one example of something you can do. You can do lock-free programming with atomics, which is where you take it like a data structure, like a queue, for example, that you might have been previously protecting with a lock, but maybe in your application, your performance was suffering because there was too much contention for the lock around that queue. So maybe you could convert the queue into a lock-free queue, get rid of all the mutexes, and rewrite it in such a way that all of the threads that are contending for that shared resource are able to do so and basically use it in a much more fine-grained way rather than taking a lock over the whole thing. But anyway, let's just kind of dive right into it. So atomics are this primitive. They're very useful, and usually programming languages provide some kind of support for them somehow. In C++, we have the standard template library, and it has this std atomic header, and that's where you can find the C++ support for atomics. As of C11, so for C programming, there's also atomics support. It might even be mentioned here. It's definitely mentioned elsewhere, even in the C++ documentation, but it's just not mentioned here. Java also has atomics. Other languages do too. I'm most familiar with C++, so that's what we're looking at today. And what is really interesting about the C++ atomics is that on these atomic objects which you create, so typically what you do is you so the atomic is a template class. That's what is provided by this library, and then you wrap another type in the atomic template. And typically you're wrapping types like an integer or a bool for a Boolean flag. There are all these type defs which make it a bit more convenient, but this is just kind of what it's doing. So typically you wrap a type. Then you have some basic operations on it, like you can load the value from the atomic and do a read, or store to the atomic and do a write, atomic read and atomic write. And those compile down to actually atomic instructions. Whatever it takes to do an atomic write or read on your hardware architecture. Architectures are different, and so there might be different ways of compiling the atomic accesses. But that's what happens. But this is a very interesting function that caught my eye. Atomic T is lock-free, and this is interesting because at kind of first glance, I assumed that atomics should always be lock-free. I thought that was the whole point of using atomics, is that you're trying, if you're using them, you're trying to, generally speaking, not use locks, or aka mutexes. If you're using atomics to do lock-free programming, that is the entire point, is to avoid locks. So it's kind of funny that this function exists, which suggests that maybe atomics do actually have locks. And it also seems like a bit of a chicken and an egg problem somehow. But after thinking about it just a little bit more, it totally makes sense, because the atomic class is a templated class, and they don't really restrict you with what type you can actually instantiate the template with, actually. The typical case is that you're supposed to be, or not supposed to, but that a typical case is, I'm looking for the constructor. So in the typical case, I don't even see what I'm looking for. There should be this thing where it's like, if it's an integer, maybe the constructor is not what I'm looking for. Integral. Yeah. Anyway, without getting too deep in those details, there is some specialization for integer types that are passed into the template class, but that's not a strict limitation. You can actually pass in potentially arbitrary types in here. And yeah, that's interesting, because those types can be of arbitrary sizes. And on a hardware level, the hardware it usually only guarantees atomic accesses up to some size. Usually it's a word size, like 64 bits on a 64-bit architecture. That will be the atomic word size. And if you're trying to do operations larger than 8 bits or 64 bits, then you can't just natively do those atomically in a single instruction. And so you could pass a massive struct with a ton of data and then wrap it in this atomic, and then start using it and expecting it to be doing atomic operations. And since it can't satisfy, like the compiler and the hardware cannot satisfy those operations with a single instruction, they need to resort to locks. And it basically becomes like a kind of interesting way to just use a mutex, actually. It's basically the same thing at that point as just declaring a mutex. and locking it and unlocking it, and then doing some access to it or modification to it in between. Let's just play around with this a little bit and just observe this. So here I have Compiler Explorer, which is very nifty, and let's just include IO stream. So I've already kind of prepped this a little bit, but I just want to comment this out for now. We'll do std atomic int atomic, and we'll print out int atomic.is lock free. And then we'll do the same thing for big atomic. And then we will execute the code. And we can see that int atomic is lock free, returns true, 1. But big atomic is lock free, returns 0. And that's because big atomic is an instantiation of the template with this big struct, which has 100 ints. It's an array of 100 ints. That is way, way, way too big to ever be modified or operated on atomically at the hardware level. And so the compilers and language still allow you to do this. I will say this is quite rare and probably kind of weird. Probably would not pass code review, really, if you really tried to do this, because it's quite, to me, it seems like quite a weird thing to do. And you'd be better off just using a mutex and a non-atomic instance of this, which is more traditional, probably more readable, more maintainable, less surprises, but it is possible still to wrap this in the atomic. But in that case, the compiler is basically just saying, okay, like you're trying to do this, and I'm going to work some magic to make this happen, but just know that it's not lock-free. And so if you were depending on this to be lock-free, please don't do that. So that's interesting. That's kind of like point number 1. It's just interesting to see that actually not all uses of the std atomic template class actually result in lock-free actions. So naturally, the next thing I wanted to do is actually kind of observe this a little bit. Just kind of observe, would it be possible to really see the locks that are generated by the compiler? One thing I want to show you is this LLVM libc++ design doc page, where they talk about the atomic header and kind of their design for it, actually. And what is kind of cool is they talk about this locking. Yeah, I haven't read this like completely so deeply, but RT. Yeah, okay. For anything the platform does not support in hardware, meaning basically large amounts of data, things that are larger than a word size. For anything that is not supported in hardware, the compiler arranges for a library call to be made, which will do the job with a mutex. And it's a library call into compiler RT, which is the runtime library that that occasionally, when the compiler emits code, it doesn't want to or can't just inline all of the instructions for a certain action. And so it will have a separate runtime library such that it can just emit a function call into the kind of companion runtime library. For Clang and LLVM, this is called compiler RT, and for GCC, it's called libgcc. And yeah, and so basically, a library call is made to this function in compiler RT, which basically just uses a lock, and it's just like a super normal like lock. And I don't actually know where the mutex is actually allocated, or how it might be shared. I would imagine, I don't really know. It probably needs to be one mutex per instantiation of the template class, maybe. I don't know the specifics of that, but the general idea is that, there's some kind of hidden mutex that is allocated that is not like visible to the user code when you're programming, but it's emitted and code genned, and then it's just literally used. So that's pretty interesting. So I was really hoping I would be able to observe this in the assembly, which is kind of what I wanted to do here. And so if we go back to our example, this is a really basic example of using the atomic class. It declares an atomic, it wraps this other type, and then it just does some very basic operations like this load from the atomic. And so big is of type struct big now. It's a normal, so big is not a stood atomic anymore. It is just a big. And we can mutate the struct, for example, if we want to, and then write it back in. This is actually not, don't actually do this code, because even though we're using an atomic, this individual sequence of actions is not atomic. Things can get interleaved in between them, which kind of defeats the point of using an atomic, but just for illustration purposes of how it looks to use this. This is kind of what it looks like with a load in a store. So my first attempt at trying to observe these locks generated in the assembly was to go to Compiler Explorer, which is pretty good for this, but I kind of ran into a wall here. It just emits this call to this function, and I wasn't really sure how to proceed there. Sometimes you can actually see, you can't see it now. Sometimes you can actually see the code gen for some other functions, but for some reason you can't here. And so I kind of hit a wall there. So then I decided to go kind of locally onto my machine, and I have this main CPP file, and I'm just compiling it with the compiler, and it produces this main binary. And then I was kind of hoping maybe I can disassemble the binary and observe it in the disassembly. That would be pretty neat. I'm using Radare 2 here, which is a free disassembler and reverse engineering tool. People kind of, clown on it or whatever, but I think it's pretty useful sometimes, and I like just using it to quickly take a look at binaries. It's a bit better than obj dump, for example. So the AAA command, analyze absolutely everything, or analyze all, analyze absolutely all. To analyze the binary, and then we can go into the disassembly here, and we're in the main function. We can see this function call atomic load. So let's hit 1. We'll dive in here. We're doing some more stuff. This looks about like what we want. Atomic load. Okay, hit 1 again. Call sim imp atomic load. Sounds good. Uh-oh. Now we are kind of going deep into the binary. We have hit a dynamic linker stub, because we're dynamically linking against this atomic load function. If we go back to the atomic load, Something like this. Yeah. Anyway, we are, because the compiler has emitted a call out into compiler RT, we're now kind of exiting the binary, and now we're kind of in the dynamic linker code that is going to call this function, but this is where it gets very dicey. And we can't really continue, unfortunately. That's good. So this is saying load, okay, get this pointer to the atomic load kind of global offset table entry or whatever the equivalent is on Mac, and then basically do an indirect branch to it, like dereference it and then jump to it. And then this is actually at this 1/4000 thing, which is actually just down here. And it's just this relocation stuff. The main point is that it's not possible to follow it beyond this point because, at least personally, I don't really know how to do it. I'm a bit stuck here. We can try seeking to this address, and yeah, honestly, I don't really know how to proceed because the code we really want to see with this locks and the code gen is not in the binary. It's in compiler RT. And no amount of disassembly of this binary is going to show it unless Radara2 is somehow like actually pulling in the dependencies of the binary. But if we use otool.l, I was actually kind of confused about this. We don't actually see compiler RT in this list. Later we'll see when we debug it that there's all sorts of other libraries that actually do get loaded into the process. But when you do a simple otool-l on Mac, you don't see any of this. And so this is all just to say that disassembling the binary is also not successful. I had another try, and I was trying to use Binary Ninja, which is a really great tool for analyzing binaries. And I uploaded my binary to their cloud disassembler because it's free, and this is ARM v8 binary, and we can do a very similar thing. We can try to follow. Okay, let's go here. Then atomic load, cool. Okay, a branch atomic load. And then we basically get into the exact same problem where we just kind of dead end at the dynamic linker data structures. Eventually, during runtime, a function pointer to atomic load will get filled in here. But when we're just statically analyzing it, we just kind of dead end. Maybe there's more elite stuff that I don't know about, but personally, I'm kind of dead ending here. And so my natural reaction when that happens is just to go reach for the debugger. And so let's just debug the binary and just step through it and then literally observe during the execution the locks that are emitted. So we can use lldb main, break main. And what I always like to do is set a stop hook, which disassembles at the current program counter, basically, and that allows you to see instruction by instruction as you're stepping through it, which is pretty useful, which is what we're going to try to do, basically. So we are in main, and this arrow points at our instructions. So let's just single step SI through the binary. Okay, we have to step into this atomic base load. Nice. Let's keep going. Stepping into this other one. Let's keep going. And we're getting close. Now we're at this atomic load thing, which we've seen many times at this point. We saw it in Radara2, and we also saw it in Binary Ninja Cloud. Let's step here. Now we're in. Now we are in the dynamic linker. If we just do a quick stack trace. I guess it doesn't really show it quite yet, but we are in that dynamic linker stub, and we are about to indirect branch into this atomic load function in compiler RT. And so we've just jumped somewhere. We're in compiler RT. And if we take a look at the stack trace, we can just confirm that. So we were in our main binary. Now we have jumped into compiler RT, into the atomic load function. And we can literally see it right here. I don't have any idea what this code is doing. Totally did not read it or anything, but you can clearly see that there are some function calls being made to some functions that look exactly like mutex functions. What's interesting is that they are not standard C++ mutexes. These look like macOS specific mutexes, which kind of makes sense since I'm on a Mac right now. But here it is. That's really it. We are literally observing the code that is kind of behind the scenes creating a mutex. And in this case, it's doing something along the lines of locking the mutex that guards our kind of quote-unquote big data. It's doing a mem copy of that data into some other variable, and then it's releasing the lock, and then it's returning that local variable, which is basically that's what the semantics are of this. The big atomic.load is an atomic copy of the data into another variable. So that is exactly it. So it's pretty neat. We've really observed that, that there's a mutex being emitted behind the scenes. Just going to quickly check back to the notes. But yeah, no, that's really it. Just wanted to share this investigation into islock free and actually how islock free can return false. And when it does, what kind of cogen happens, which is exactly this kind of cogen in the compiler support library. So that's it. That's everything I know about how atomics can actually be not lock free. Thanks for watching.